In this lecture, we will be continuing the discussion on a solution of linear algebraic equation. In the last class, we have discussed on Gauss elimination method and back substitution. And in this lecture, we'll start with the discussion of another algorithm, which is Tridiagonal Matrix algorithm. This particular algorithm similar to Gauss elimination, but the format of the coefficient matrix is a special kind, where other than uh, the principal diagonal and two neighboring diagonal elements which are non-zero and most of the terms are zero, that's why we can eliminate a lot of calculations from the Gauss elimination if we follow this particular algorithm. And this particular format of tridiagonal format is very common in CFD applications. We know that a physical phenomena, uh, many mechanical applications, uh, those can be described by partial differential equation, and if we discretized those equations, and it is possible to get that uh, after discretization we can convert the partial differential equations into set of linear algebraic equations, and those linear algebraic equations looks very similar to this tridiagonal format, and that's why solution of this particular format, if it is a less expensive one than the Gauss elimination method, then definitely it is very useful for the engineers. Let us start with one example, one physical example, and then we'll see that how from that physical example we'll come up with this particular format. So let us take one example where we can consider that this is a fin, and the heat is transferring through conduction through the fin and through convection from the surface of the fin. So the governing equation of this particular fin problem is, if we write, it will be of this form in a steady state format, is d2t dx2 minus m square into t minus t infinity, which is equal to 0, where this m square is basically convective heat transfer coefficient into the perimeter of the cross section divided by thermal conductivity of the solid fin and the cross sectional area, and we are assuming that the cross sectional area is constant throughout the length of the fin. So this is what is m square. So this is the governing equation, and if we discretize this equation, using central difference scheme for the second order derivative, we will get the format or the set of algebraic equations. You see that how can convert these governing equations into set of algebraic equations. We just write this d2t dx2 by central difference scheme for any intermediate grid points. If we divide the whole length of the fin into total 11 number of grid points, so this is grid point 1, grid point 2, grid point 3, like that, and finally at this end it is grid point 11, and this is grid point 1, and from 2 to 10 these are intermediate grid points. So for any intermediate grid points, that means for I is equal to 2 to 10, what you can write for any intermediate grid point, you can write using central difference scheme for this second order derivative. You can write it is t I plus 1 minus 2 ti plus ti minus 1 divided by delta x whole square, where delta x is the distance between any two grid point. And this is what is the central difference scheme, how we can discretize the second order derivative. This m square t we can write simply m square t at the ith point, and this part is basically a constant. This whole part is a constant, which is a known quantity actually. So now if you simplify after multiplying by delta x square, if you simplify, you will end up with the equation of the form ti plus 1, then minus 2ti, and this is m square ti into delta x square, because you have multiplied by delta x square. And if you write this delta x square into m square as alpha, then it is minus 2 plus alpha into ti, where this alpha is what? That is m square into delta x square. Okay, and plus ti minus 1, and that is equal to minus of m square t infinity into delta x square. The whole thing you can replace by a quantity beta. So for any intermediate point you can see, so what is beta? This beta is basically minus m square t infinity into delta x square. Okay, so this quantity. So if you just simplify, you will get this format. So for any intermediate point, for I is equal to 2 to 10, in this case these are the intermediate grid points, you can write this equation. So that the same equation has been written here. You can see the set of equations that we have to solve for the temperature, where this is for, you see, the grid point 2, this is for grid point 3, this is for grid point 4. These are the equations. So if you just put I is equal to 2, you will get this equation. If you put I is equal to 3, you will get this equation. Okay. So these are for the intermediate points, and for the endpoints, for the 1 and for the 11, maybe some boundary conditions are given. It is known, suppose the temperature at the base of the fin or the temperature at the free end, these are known. If this kind of Dirichlet boundary conditions are given, so those boundary conditions you can write like this, that T1 is equal to 100, maybe this temperature is 100, and it is given that T11, that is 25. So this kind of informations are known. So here you can see that this is a physical, this set of algebraic equation actually represents a physical problem. So if you can solve this set of equations, you will get the temperature field. So how the temperature is vary along the field from the base to the free end. So now to solve these algebraic equations, and if you just simply write this in the matrix form, AT is equal to B, in that form, if you just simply write it is in the form AT is equal to B, where A is the coefficient matrix, you will find clearly that this A will be a tridiagonal matrix. Okay, so the general form of the tridiagonal matrix, as you can see here, it is basically the principal diagonal terms which are represented by D1, D2 like that, and the upper diagonals are U1, U2, and the lower diagonals are L1, L2 like that, and all the other terms are 0. Okay, so this is the special format that is there. Now after understanding the problem, let us try to solve this particular equation. So the first step of solving this equation is that create this particular coefficient matrix first. So creating that coefficient matrix is done here in these few steps. As you can see, initialize by zeros first, and then these alpha beta values which are given. Using that, this using a for loop, this coefficient matrix is generated, and the augmented matrix AB is also created. But in this for loop, definitely some of the values are not actually in the correct position. So those who are like boundary conditions, are some of the other values are replaced, so that you get the final uh, coefficient matrix and the augmented matrix. So AB is the augmented matrix where the coefficient and the non-homogeneous part is taken together. So in this way, first of all, we have to create the whole matrix. This is the first step. And definitely once the matrix is created, you can definitely find out the temperature field by A/B by this format. But we are not going to use this one. Just to check the final result, I have just calculated here. We are going to use the tridiagonal matrix algorithm. Now see, the tridiagonal matrix algorithm is, as I have told you, that it is similar to the Gauss elimination method. So we will look for the pivot element, then we'll try to make it as a upper diagonal, upper triangular matrix. We'll try to make it a upper triangular matrix, and then back substitution we'll try to solve it. So let us see that what is this tridiagonal matrix algorithm. So if you just write the equation is of this form, you can see that a11 into x1 plus a12 into x2, and all other terms are 0 basically in the first equation, and that is equal to b1. Okay, or if we write simply small b1 is equal to b1. The second equation is like a21 x1 plus a22 x2 plus a23 x3, and all other terms are 0. All the remaining terms are 0 and is equal to b2. The third row will be like a31, but this x1 is 0 in that case because it is a tridiagonal matrix, so that part will not be there. That will be 0. So what will be there is a32 x2 plus a33 x3 plus a34 x4, and then all the terms are 0, and that is equal to b3, and in this way it will go on. So this is what is the format of the tridiagonal matrix. Okay, right? So what we are going to do, that the first step is that we are going to divide the with the pivot element. So which one is the pivot element? A11 is the pivot element. So the first step is that you just simply divide with the pivot element. So all the term, if you divide with the pivot element, then this is the first step. You divide by the pivot element. So if you divide by the pivot element, then what this term will become, that is a12 divided by a1. So that has been done here. You see that I comma I plus 1. So when I is equal to 1, it is basically a12. So this particular term a12 divided by a11. And what will be this term? This b1 will be replaced by b1 by a11. So that is this equation, this line. And then what will be this first term? This first term will become 1. So that is why this term will become 1. That has been written. So this is the next step. What is the next step? Our objective of doing this is basically to make this part 0. So we want to make this term 0. Okay, so that we can make it is upper triangular matrix. There will be no term in the lower triangular part. So everything will be 0 in the lower triangular part. So what we are going to do, we want to make this quantity 0. So to make this quantity 0, we let us take this quantity a to 1, a to 1, and we multiply this a to 1 with the whole row, this complete first row. You multiply it with a to 1, and then this quantity already become 1. When you multiply it by a to 1, then this two term will become same. So you subtract this row from this particular row. So basically your operation in case of a Gauss elimination, if you remember, this R2 was R2 minus this quantity a to 1 into, now after dividing with a11, what is the remaining row? Okay, so previous R1 divided by a11. Basically this operation was there in case of a Gauss elimination. Now already we have divided by a11, so you just simply, if you write this a21 as alpha, I have given the name alpha as a21. So you just multiply all this term with alpha. So what is done, you observe that this term is multiplied with alpha and subtracted from this term. Okay, so this a22 here, this is a22x2. This particular term will become what? A22 minus this previous term, that is previously which was a12, now divided by a11, that is the new a12. So that quantity is multiplied with alpha. So what is this alpha? This alpha is nothing but a21. So it is multiplied, and after subtracting you will get the new value of a22. So that is basically done. You observe here that what will be a22, that is the previous a22 minus alpha, alpha is this particular value, multiplied by the new value of a12. New value of a12 is what? A12 by a11. That has been stored already here. Okay, so in this way this row value has been changed according to this formula. Then what else? You need not to do with this value, because here it is 0. So whatever you multiply with 0, it will become 0. So when if you subtract, everything will be 0 here. So you need not to do with this one, need not to do anything with a23. So only thing that you have to do with this one, and you have to do with b2, because the same thing you have to do with b2. You have to multiply it by alpha and b2 minus, so previous b2 minus alpha into the new b1 that you have already created here. So when that is done, the final thing is that all the other terms are 0, so you need not to do anything. Only the first term will become 0, so that you put as 0. The first term a21, that is now 0, so you just put that quantity 0. So this is what you have to do in each and every steps for each and every row. So that is why this I goes from 1 to n minus 1, and the same thing is repeated. And if you do in that way, it will be converted into upper triangular matrix. So in this way, a lot of calculations we can avoid of the Gauss elimination, because all the other terms are 0, so need not to do the complete row operations, only the few terms that you have to manipulate. Next, after completing that, you can see this upper triangular matrix has been formed, and finally what you have to do is that you have to back substitute. Again in the back substitution, you need not to do the whole process in the that we have done in case of a Gauss elimination. You first initialize the temperature field as 0, and then you find out the last temperature, the Tn. Okay, the last temperature Tn, that will be simply Bn by Ann, because in that case only the Ann will be there. Ann into Tn is equal to Bn in that form. This is the last term. So Tn you can directly find out Bn by N. And what was there in the previous term? Definitely in the previous term it will be a n minus 1. Okay, a n minus 1 will be there, and a n minus 1 in a n minus 1 in into t n minus 1, and that will also contain quantities like a n minus 1, t n minus 1, t n minus 1. So it is going to contain a n minus 1 n minus 1. This is the diagonal term tn minus 1, and that n minus 1 n tn is equal to bn minus 1. So you see that already in the last term where a n n tn is equal to bn, where already you know what is tn. So you just put the value of tn here and you will find out what is tn minus 1. So in this way, if you observe that you know the previous value, if you know the last value before that, using that you can find out that particular value. So that has been done. You see that I started from n minus 1, and with an increment of minus 1 it goes up to 1, and ti will be equal to what? That will be bi, that will be bi minus a I comma I plus 1, that value I comma I plus 1, that value into ti plus 1, because ti plus 1 already calculated, because you are now trying to calculate ti. Okay, so when you are trying to calculate n minus 1, already n is calculated. So when n and n minus 1 calculated, when you try to calculate n minus 2, already n minus 1 calculated. So using the value of n minus 1, tn minus 1, you can find out tn minus 2. In this way, gradually from the bottom to top, you will be able to find out all the temperatures. So this is what is the algorithm. So if you can finally find out, you will get the same result, and you can also plot that to see that how temperature is varying along the length of the feed. Now, after understanding this direct method of TDMA, let us see uh, the iterative method of solving the linear system of equations, which is very useful technique, or the iterative methods are very popular because in this kind of a method, by iterations, we can solve very easily without um, because the algorithms are much more easier and very quickly it converges. Now see that there are two kinds of iterative method as described here. One is the Jacobi, another one is the Gauss-Seidel method. In Jacobi's iteration, if you see, or in the Gauss-Seidel, basically in the superscript what is written, it is basically the iteration number, and in the subscript what is written is the variable number that you are solving. Let's take one example and through that try to understand. Here three equations are given, right? Equation 1, equation 2, and equation 3. So here basically one important thing is that when you are finding out the variable 1, then you are using equation 1. When you are finding variable 2, you are using equation 2. When you are finding variable 3, you are using equation 3. So this is basically the idea that you have to remember. So that is why the order of equation is very important, and because you are finding out the variables from those order of equations, and that is why one of the technique is important, that is the diagonal dominance. So order the equation. The first step is the ordering of the equations. So ordering of the equations is recommended that you order it according to the diagonal dominance. By diagonal dominance, I mean that the principal diagonal terms, when you form that coefficient matrix, should be the dominating one. Okay, so that should dominate. It is not that all the time you will get this kind of preference. Sometimes this perfect diagonal dominance will not come into the picture, but if possible, if you get this kind of a diagonal dominance, then the convergence will be high. So try to arrange these equations in the form of diagonal dominance. But what is the idea? What is the difference between the Jacobi and the Gauss-Seidel? Let us try to understand that first. Okay, so let us order the equations in this way so that we can get some amount of diagonal dominance. It is clearly that it is not a completely diagonal dominance we are getting, but still we are getting some kind of a diagonal dominance like 2, 4, 1. These are the diagonal terms, so they have certain dominance over the other terms somehow. So the idea is that, so from equation 1, so now this is our equation 1, this is equation 2, and this is equation 3. So from equation 1 we will find out x1. So what is x1? Simple, 7 minus x2 minus 3x3, that divided by 2. Similarly, what will be x2? x2 will be 9 minus plus 2x3 minus 3x1 divided by 4. Similarly, you can find out what is x3, which is 4 minus x1 minus x2 divided by 1. So this is what is the x1, x2, x3 that we can write in terms of the other variables. Okay, so we have used to find out x1 equation 1, to find x2 we have used equation 2, to find x3 we have used equation 3. Now see that what is the technique in the iterative method. Initially you guess some value of x1, x2, x3. Let us guess x1 is equal to 0, x2 is equal to 0, and x3 is equal to 0. So this is the guess value, initial guess. This is the initial guess. So always in an iterative method, we start with some initial guess, and then using these guess values, first calculate what is x1. So in the iteration 1, the first iteration x1 1, you just put x2 as 0 and x3 as 0. So if you put x2 and x3 as 0, which is our initial case, you will get some value of x1, and that is 7 by 2 or 3.5. Similarly, to find out x2, what we can do, we can put the value of the initial guess x3 and x1, and we get the first iteration of x2. So in that case, we'll get 9 by 4. And here if we put the initial guess of x1 and x2 and we find out x3 of the first iteration, we'll get 4 by 1. So in this way, if we find out the x1, x2 and x3 after first iteration, then this method is called the Jacobi's method. So in Jacobi's method, what we are doing, we have used the values of x1, x2, x3 of the previous iteration, or previously what was the values that we have taken. Using that we are finding out the current iteration. But in case of a Gauss-Seidel method, what we are going to do, to find out the first iteration x1 first, we are going to use x2 and x3 as 0. Okay, no issue, that will be same. But when we are trying to find out x2 first iteration, at that time we do not have any other values of x3, so we'll put x3 is equal to 0. But this x1, instead of putting the initial guess x1 is equal to 0, we are going to put the already updated value in the first iteration, that is 7 by 2. So always we try to update our data. We are not going to wait for the complete iteration and then we are going to update in the next iteration, which we do in case of Jacobi's iteration. Here what we are going to do, every time the values are updated, we are going to use that. So when you are finding out the first iteration of x3 in case of Gauss-Seidel method, in place of x1 and x2, we are not going to put this 0 and 0. We are going to put already found out value of x1 and x2 in the same iteration. So here you see that in the formula, that in case of a Jacobi's method, when you are finding out the xk of the I plus 1th iteration, all the x values that you are using of the previous iteration, that means ith iteration. But when you are, in case of a Gauss-Seidel method, when you are finding the values of xk in the I plus 1th iteration, you see you are using already calculated values of x in the same iteration and the values of x that you have not calculated yet. So that is why you are using the previous iteration values. So in this way the Gauss-Seidel method will converge very fast. So Gauss-Seidel method is much more useful and can very quickly get the solution. So I hope the concept is clear to you. Now let us try to apply this into the algorithm. So first step is that you order the equations according to the diagonal dominance as much as possible. After that, you create the coefficient matrix and write the B matrix, create the augmented matrix, and then basically you define certain, initialize this x as zeros, that is the initial case that you consider. You initialize error, number of iteration you specify. Let us see that what will be the result after 25 iterations. So that is why here we have defined number of iterations, and you define some error initially as 0, and that is going to be updated over the iterations. So in the main loop, if you observe, where what we are doing is that in a Gauss-Seidel iteration, that this xk, that is basically how it is calculated. As you have observed that it is kind of a k1 x1 plus a k2 x2 in this way, then maybe a k minus 1 x k minus 1 plus a k xk, and plus a k plus 1 xk plus 1 a k plus 2 xk plus 2, and finally in this way akn xn, and that is equal to bn. It is of this form. So I have written the nth equation. Okay, I have written the nth equation where from we are finding out xk. Xk is the diagonal term. Okay, so so what will be xk then? So definitely xk will be equal to bn minus, it is clear, it is the bn. So what is the bn? Bn is basically, if you see the augmented matrix, it is the last term in the augmented matrix, because augmented matrix contains both a and b. So in the kth row, it is the last term that will take basically the bn. So this quantity then minus ab k comma 1 to k minus 1. That means bn minus all these values which are actually coming from the, all these x's are coming from the equations which are uh, before xk. So already these are updated in that current iteration. So for those values you just uh, put the values of the current iteration, so into x1 to k minus 1. So basically this matrix multiplication indicates nothing but ak1 x1 plus ak2 x2, like that. And then minus of this part, the k values which are not already updated. Okay, so the k values which are used for the remaining, those are not updated and are basically using the previous values of x. Okay, and these coefficients are there. So in this way you just divide by akk and you will get xk. Okay, so this is how the in Gauss-Seidel method you can find out the x. Finally, for the error, after one particular iteration, when all the x values in that iteration is calculated, then the maximum of all the values is taken as the error. Maximum of all the values is taken as the error. As you can see, that error is defined as x old minus xk, because every time the xold is defined. So xold, and then after that xk is modified. So xold minus xk goes into the error. So for each of the x1 to xn, all the values, uh, you are going to get some error. So the maximum of this is actually stored as error in that particular iteration. Okay, so once that is done, and after that the same iteration will go for the second iteration, third iteration in this way, and we can put a limit of the iteration. Here I have given that limit as iter is equal to 25, so it is going to do the calculations for the 25 iterations, and finally after iterations, if we see the result of the calculation, you see here that for iteration number 1, what was the error, and gradually the error is decreasing, and finally the values of x you can also see, and you can also plot the error, how the error is changing. You can see after 10 or 12 iterations the error is almost zero. So this is what is the Gauss-Seidel method. One small assignment is there, that try to write the code for the Jacobi iteration of the same problem. Thank you.